Hello community, Variational Autoencoder. It is the statistical grandpa of our autoencoders, but also a very important part if you want to understand autoencoders, because they are not the typical autoencoder that you might know. So let's have a look in detail. What is it? Now, it belongs to the family of probabilistic and graphical models. So, probabilistic means we are here in mathematical probability theory, and graphical means we're in graph theory models. So, you already can see there's something different. But the really important piece is here, the sentence. Given an input sentence x characterized by an unknown probability distribution p of x, the objective is to model or to approximate the data's true distribution P. So as you can see, we are here not dealing with hard facts, but with unknown probability distributions. Now, if you remember what I told you in my last two videos about autoencoders, there's roughly the same architecture, the same design here. We have an input space where we have our input data, we have a neural network, and then we have a latent space. This is a condensed space, a lower dimensional space, where the information content of the latent space should be equivalent to the information content of our input space. You go from the input space over the neural network to latent space and back from the latent space to the input space. And this is, of course, done with backpropagation. So you compare your input to your output if you run more or less from an input space with high dimension to a low dimensional space. And then, of course, what you can do is you can compare the projection you get from your decoder. Decoder we call the run back from the latent space to the input space. It's the decoder. And the first run from the input space to the latent space is, as I showed you in my old videos, the encoder. You can combine now these two images, you find the error, you have a loss function defined, and therefore you can train your network. Now there are two main items you should be aware of with variational autoencoder. At first, probability theory. You know that here, if you go from input space, latent space, and back and forth with backpropagation, the normal backpropagation will not work. You need something like a stochastic backpropagation. This is a mathematical, really challenging approach, and the second part is here in our loss function. If you compare now the projected result from the first run when you train your neural network, we will have to add a second loss term. We call it a divergence. So we have the classical loss term and then the additional divergence term. For our loss function, we train our loss function to be minimized, and then we have the minimal error and the weights in our neural network are trained. If you want to learn more about statistic backpropagation, there's this beautiful archive paper from May 2014 from Google and DeepMind about stochastic backpropagation, and you have a mathematical introduction into the topic, but be warned, it takes half an hour to an hour. So let's summarize it. We have two additional points. We have a divergence, or if you call it a relative entropy, a statistical distance. Now, what is it? A very simple explanation would be, it is just a measure of how one probability distribution P of our input data is different from a second reference probability distribution Q. So, and since we have two probability distribution, you know it's just not a distance, but it is a squared distance. And in mathematics, we call this, as a generalization, a type of divergence. That's the reason why we call this a divergence term in the loss function. And the second part, of course, is that we know that backpropagation needs now the stochastic backpropagation. We introduce an epsilon function, and there's a specific path for the epsilon function to be optimized. So these are the two terms you have to be familiar with if you do this. Now, a beautiful introduction to variational autoencoders by Max Welling. This is really an in-depth introduction to variational autoencoders. But now, here on our COLAB notebook, this is an official Keras notebook. I leave you the link here and in the description so you can follow along if you want. Variational autoencoder. So let's start with the beginning. We have a classical setup and we do convolutional autoencoder here trained on our MNIST digit dataset. We import our library, our TensorFlow, our keras layers, and then, as you know, we have to have a sampling layer. Now, this sampling layer we can use in a variety of the topics, but since it's a probability distribution, we have to define our sampling strategy. This is here done for you with the epsilon defined as the keras backend random normal. So, having done this, we can now build the encoder and the decoder. We follow the typical design of an autoencoder. The latent dimension is 2. This means we will decrease our latent space to a 2-dimensional configuration with 2 units. We have our input defined 28 pixels times 28 pixels. And in the other videos I showed you, we have a convolution 2D keras layer that is doing all the convolution and the things with us. We have a ReLU activation function, and our stride width padding is 2 and padding is the same. We have, of course, then our sampling, and the keras model finally is our encoder input and our calculated sampling technology. We can name this our encoder. And if you would like to see how our encoder looks like now from the different layers, we have the command encoder.summary. Now here you see all the different layers that are now we have designed now. We have input layer, convolution 2D layer, everything coming down from the dimension, then we flatten everything. And then we have our mean and log variance layer. And of course, the sampling then finally is done. And yes, you can see here the number of the parameters and whatever is connected to these layers. Now for the decoder, we do exactly the same thing in the reverse order. Now, if you look for the decoder, our keras input layer or input is, of course, the latent dimension that we defined in our encoder. So we start from the latent space and we go backwards through our stochastic gradient descent to the input space. So what we do, again, we have dense layers, we reshape, and then we have our convolutional 2D transpose layer. Remember, this is the transpose as I showed you in the last video. Then we have defined our output layer, and our complete keras decoder model is now with the latent inputs. Of course, we go from the input space, from the latent space to the input space, and our decoder outputs is the output. We call it a decoder. And if we run again, now the summary command, you can see now here in detail our different layers. This more or less goes reverse to our encoder layer structure. And now we are finally ready. We define our variational autoencoder. We have our encoder, we have our decoder, we have the total loss tracker. You can see here named total loss, and the reconstruction loss tracker. And then we have here this beautiful term from the divergence. This we call KL loss for the divergent term we identified before. We have defined, of course, here a metric, and then we go here to our training steps. Now, here, just to show you, we have here our decoder, our reconstruction loss that is defined. Then here in the next line, as you will see, we have now the KL loss function defined, and our total loss is the reconstruction loss plus this additional term, this divergence, this KL loss term. So we have 2 terms in our loss function that we have to calculate. Isn't this beautiful? With this now defined, we can now go on further. We can define an optimizer, apply gradients, have an update on the tracker, and as a return function, what we will get 3 terms. We will get the total loss, we can get the reconstruction loss, and we get the divergent loss if you want. So we have every term we want, and the next step is finally train our variational autoencoder. At first, we have to download the dataset. We go here with the MNIST load data command. We concatenate it, expand the dimension a little bit. And here now we have finished our input data step. And now finally, we have defined the model of our variational encoder and decoder. We compile the function and we define the fit command. So let's run this. And as you can see, I forgot to activate this cell, so we have to do it again. And as you can see from our 30 epochs, we now make a short jump in the future. And I hope to show you that after, yes, 28 runs epochs, we are now close to finish. And the next step, what we're gonna do is display a grid of now the sampled digits. So just waiting to finish. Yes, we have finished it. And now here we go. We plot now the different figures from our sampled input from the latent space. And we just use a matplotlib function, as you can see here. This is the code from the notebook. You can modify it however you want to do it. This is just for demonstration purposes. So we just plot the label. We just have a grayscale visualization here. Of course, our data set is in gray. And we are just waiting for the program to finish. Come on, let's show me the figures. How does it look like? And yes, here we go. Oh, finally. Okay, you can see here now exactly, wow, how those figures merge into each other, more or less. We start with the 1s, then we suddenly transfer to the 5. Oh, wow, this is interesting. From 5 to 0. Now this is great. 4, 4, 8, 5, 6. Interesting. Okay, you can play around with this. You can have a look at this in detail. But here we just display how the latent space clusters now the different digit classes. Remember, and if you look at this, and this is just a matplot scatter visualization. Hey, yeah, it doesn't look so bad. I mean, yeah, this is the label clusters. Yes, if you increase the training, you can get better. But I think for our demonstration purposes, you can clearly see the clustered structure here of our MNIST dataset. So this was it. Very short introduction. You have the complete code if you want in the official Keras notebook. And if you want to run through all of this, yes, we have to go back out of the GPU because we don't want to take any free resources from somebody else who needs this. So variational autoencoders, I think a very, very interesting topic. It became famous in 2020, 2021. And as you can see here, we have now the homepage of Keras, and here you can see under generative deep learning, you have here variational autoencoders, a complete notebook ready for you with here the different chapters. You have a tutorial here on the homepage of Keras, but if you want, you can have a direct look in COLAB, jump to your COLAB notebook, or if you want the source code, there's also the GitHub link available for you. So variational autoencoder is just the first step. As you can see here in generative deep learning, it's number 1. But then for our other GANs, we have a lot of other Keras implementations already for you. So if you are interested in a conditional GAN or in a cycle GAN or whatever you're looking for, this is it. Hey, there's even some vector quantized variational autoencoders. Hey, I'm not familiar with this. Now, this is interesting. Okay, so as you can see, a lot of stuff to learn, already done for you, programmed for you. Give it a try. Explore autoencoders.